Hello, good morning. Bismillah. So today we will solve the final exam of Physics 2. Please read the question carefully, solve them, and you circle the right answer. Let's start by question number 1. How much energy is stored by the group of capacitors shown below if the voltage between A and B is 100 volts and each capacitor has a capacitance of 5 microfarad? Okay, so if I want the energy stored, I need to calculate. So it's half C equivalent V squared. In other words, it will be half. What is C equivalent? We need to calculate it. What is V squared is 100 volts squared. So the idea is to calculate C equivalent. So C equivalent is C between A and B. Okay, so how to calculate the equivalent capacitor or capacitor here? Let me call them 1, 2, 3, 4, and 5. If I want the equivalent capacitance, I have to first combine these two. Okay, because 4 and 5 are in series. These two are in series. Okay, and then these two are in series. I combine them to get C45. Then it's in parallel with 2. Parallel with 2. So this will give me C245. Then C245, which is here, is in series with 1 and 3. So this in series with 1 and in series with 3. Great. So let's start by C45. There are only 2 of them, and they're in series. When capacitors are in series, you have to take the reciprocal and add them. 1 over C4 plus 1 over C5, and then you take the inverse or the reciprocal of that. If it's only 2, it's just product divided by sum. Basically, C4, C5 divided by C4 plus C5. Here, by the way, all the C's are the same. C1 equal to C2 equal to C3 equal to C4 equal to C5 equal to C, it's equal to 5 microfarad. Even here, they're all identical. So C45 is half C. Product divided by sum. So this is 2.5 microfarad. Okay, good. And that's in parallel. Now C45 is in parallel with C2. And this gives me C245. When they're in parallel, you just add them. This is C2 plus C45. This gives me 7.5 microfarad. In other words, okay, so let me do it here in blue maybe. So this was 1, this was 2, this is 3, this is 4, and this is 5. So all these, I combine them, I replace them by C245, and that's 7.5 microfarad. And you see now here I have something like this. I have C1, C245, and here I have what? C3 between A and B. So what is now the equivalent capacitor? Well, 1 over C equivalent will be equal to 1 over C1 plus 1 over C3 plus 1 over C245. In other words, this gives you 1 over 5 microfarad at 2 times. These two are the same. Multiply by 1 over 7.5. So you do the calculation and you find that C equivalent is the reciprocal of all this. If you do it properly, you find 15 divided by 8 microfarad. Okay. So between A and B, I have one single capacitance of C equivalent, which is 15 divided by 8 microfarad. Now, if I apply a voltage of 100 volts, let's calculate the energy stored. It will be 1/2 of C equivalent, which is 15 divided by 8, 10 to the power minus 6 farad times 100 squared. 100 squared. And if you do the calculation, you find that it will be equal to 9.4 10 to the power minus 3 joule. You put everything in SI units, this in farad, this in volt, you will have joules. So this gives you 9.4 millijoule. So A is the correct answer. Let's look at the second problem here. Read it carefully. So here we have cross fields. E is perpendicular to B. E is along the direction of K hat in the Z direction, and B is along the direction of J hat. Now we have an electron. We know the mass of the electron. Look in the formula sheet, 9.1 10 to the power minus 31 kilogram. And we know the charge of an electron minus E, 1.6 minus 1.6, 10 to the power minus 19 coulomb. With kinetic energy of this? Well, if kinetic energy K is 250 eV, 251 eV is 1.6 10 to the power minus 19 joule. And this should be equal to half mass of the electron times the velocity of the electron squared. So that means if I want the velocity of the electron, I just take square root of 2 times the kinetic energy in joule divided by the mass of the electron. So we put the kinetic energy in joule, right? By multiplying by 1.6 10 to the power minus 19. Okay, so the speed gives us something like 9.38 10 to the power 6 meters per second. That's the speed. And I'm just exploiting the data of the problem. So by giving you the kinetic energy of the electron, I'm giving you the speed of the electron. V is, and we calculated it, 9.36 or 38, sorry, 9.38 according to my calculation, 10 to the power 6 meters per second. Okay, the electron is moving in the negative direction, enters a region where both of this electric field and magnetic field are present. Find the value of E such that the electron is not deflected. So if I don't want the electron to be deflected, I need the total force, which is the Lorentz force, which is due to the force of the electric field, due to the electric field, and force due to the magnetic field. Basically, this is charge of the electron, which is minus E, times the electric field plus V vectorial the magnetic field, or cos the magnetic field. Okay, so I want this to be 0. So if this is 0, that means this has to be 0. E plus V cos B has to be 0. Does it make sense? Yes, it makes sense. It can be 0. Why? Because E is along the K vector, is plus Z. V is in the negative X direction. This is minus I hat. Cos B is along the J direction. So basically, the first term is along K. What is minus I hat J hat? This is minus K. Okay, so that means the electric field and the V cross B are in opposite direction. If they are in opposite directions, they can cancel each other. So they can cancel each other. So I check the direction. This is along K direction. This is along K hat direction, minus K hat direction. So they can cancel each other. Now, in magnitude, they have to be equal, meaning the magnitude of E has to be equal to the magnitude of V cross B, which is VB sine the angle between V and B, which is 90 degrees, which is 1. In other words, the electric field has to be equal to VB. That's why we call it velocity selector, if you remember. Okay, let's put everything in SI units and calculate. We know V, it's this. We know B, it's 10 microtesla, which is minus 10 to the power minus 2 Tesla. You do the calculation, your answer will be C, 9.38, 10 to the power 4 volt per meter. That's the magnitude of the electric field to cancel the net force on the electron. Great, next question. So read it carefully. So here we have a cylindrical capacitor, okay? So, and I want the capacitance of the capacitor. So if I have a cylindrical capacitor, you look at the formula sheet. We have demonstrated that the capacitance can be written as 2 pi epsilon naught length of the cylinder divided by length of B divided by A. B being the outer radius and A being the inner radius. So here they are separated by A. So let's just calculate. So this is just a direct calculation. Pi times 8.85 10 to the power minus 11. Okay, that's epsilon naught. You remember epsilon naught, right? So you can check it in your formula sheet. Epsilon naught is given in your formula sheet, 10 to the power minus 12, sorry. And then you multiply by the length. The length is given 12 centimeters, so 0.12 meters, divided by length outer radius B, which is 0.3 divided by 0.25. You do the calculation and you will find a capacitance of 37 picofarad. Let's look at the next problem. So in question 3, you notice that this is it. Great. Question 4, read the question carefully and we solve it. So this voltage for U, let me call it U. The voltage, let me call it V. It's 115 volts. It's applied across this cylindrical wire. So you see here, the delta V, which is the V, is 115 volts. I gave you the length, by the way. What is the length of the wire? It's 10 meters. And I give you also the radius. So you can calculate the cross-sectional area. So the radius is 0.3 10 to the power minus 3 meters. And I give you the magnitude of the current density. So the current density J is 1.4 10 to the power 8 amp per meter squared. Question, find me the resistivity of the wire, rho, in ohm meters. Okay, so how can we do the calculation? How many formulas? Okay, you can use Ohm's law if you want. You can use macroscopic Ohm's law, you can use microscopic Ohm's law. macroscopic Ohm's law is V is Ri. If you want to use this, but you can also use microscopic Ohm's law, which is what? So I can say, for instance, J is sigma times electric field. Or I say current density J is 1 over rho times electric field. Okay, that's what I will use, by the way, here. You have many ways, okay, many formulas to get the right answer. So here I will use this Ohm's law. Current density J is electric field divided by rho, meaning rho is the resistivity, is electric field divided by current density J. So rho is electric field. What is electric field? You remember, electric field is V divided by L. That's why it's in volt per meter. Okay? Divided by J. So I know V, 115. I know L, 10 meters. And I divide by J, 1.4, 10 to the power 8. And this will give you the answer to the question. And the answer is 8.2, 10 to the power minus 8 ohm meter. Okay, good. Next question. So I ask you to read this problem very carefully. I have a charge particle. And I give you the charge, 7e. So E being 1.6 10 to the power minus 19. And I give you the mass of the particle in kilograms. And it's accelerated from rest. It's a positive charge. And it's accelerated from rest through a potential difference of 220 volts. Okay, let's exploit that. Let's look at it here. I have a positive charge, which is initially at rest, plus Q. And it's accelerated. That means it's attracted by this and repelled by this. Obviously, yes, because the electric field is towards lower potential. So it's attracted in this direction. So it's accelerated through this direction. So Fe is Me, Ma. But it's also QE. So it's accelerated in this direction. Anyway, it started from initial velocity, which is 0. Question first, what's the final velocity here? Interesting. Well, what I have to do, conservation of mechanical energy, because I have a conservative system. Delta K plus delta U is equal to 0. So half mv final squared minus half mv initial squared, which is 0, plus Q delta V, which is potential V final minus potential V initial. So V final is negative, the potential here. Let me take it as V0. V initial, I will take it to be 220 volts. You see, delta V is V final minus V initial is minus 220 volts. Be careful. You understand why? Good. Because the electric field is lower towards lower potential. So the potential here is 220 lower than the potential here. And this has to be equal to 0. In other words, half mv final squared is minus Q times, so if I say final is 0, initially is minus 220. Yes, this is what I have to find. And this is equal to plus Q delta V, basically plus QV, which is 220 volts. Okay. So delta V here is that's what I call yeah, you get it. Basically, this V here, you have minus minus, so it's plus 220 volts. In other words, if I say, and this is equal to half mV final squared, that means that V final is square root of 2 times QV divided by m of the electron. So that's the velocity. I mean, that's the speed of the electron. Great. You can calculate it. Let's calculate it. Square root of 2. Q of an electron, I mean, absolute value, of course. I'm talking about absolute value. Sorry, it's not an electron. Let me redo it. So this mass is not the mass of an electron. The mass here, m. You will agree. So it's 2 times Q. Q is 7 times 1.6 10 to the power minus 19 times the voltage. The voltage difference is 220 volts. And I divide by the mass. And the mass is given, it's not an electron, 1.16 10 to the power minus 26. And you can do the calculation. Okay. So it then enters a magnetic field, a uniform magnetic field perpendicular to the velocity. So I will have cyclotron motion, basically an orbital motion. And I give you the magnitude of the magnetic field. Question, what is the radius of the particle's orbit around the magnetic field? We talked about this in class. R will be mv divided by qb. This is the formula you have to use. M, we know it. It's this M here. V, we know it. It's this V here. Q, we know it is 7 times the elementary charge. And B, we know it. B is here. You do the calculation and you find it will be 2.95 millimeters. That's the radius of the particle's orbit. Is it clear? Good. Now here, first thing you have to do is to find the speed, which is 2 times QV divided by the mass. The mass is this, Q is this, and you put everything in SI units and you have the speed. Once you have the speed and you have the magnitude of the magnetic field, you can say that the radius is mv, mass times the speed divided by qb. I know the mass, it's here. I know the speed, it's calculated here. I know q, it's 7e, and I know b, 0.723 Tesla. And this will give you 2.95 10 to the power minus 3 meters is 2.95 millimeters. If you don't remember this formula, where we took it from, this comes from the fact that your magnetic force FB, which is QVB, sine 90, which is 1, is a centripetal force, which is mv squared over r. When simplifying by v, you end up with the radius of your orbit is this. Okay, good. Now let's solve this problem here. Read it carefully, and then we solve it. C1 is equal to C3, C2 is equal to C4. Let's find C equivalent. So here, these two are in parallel. So I will say C2 in parallel with C4 and in series with C1 in series with C3. So when they are in parallel, you multiply and you divide. Basically, it will be C2, C4 divided by C2 plus C4. So these two will give me C24 product divided by sum. So it will be just half. So this will give me just 3 microfarad. Okay, so this is 3 microfarad in series with C1, in series with C3. So the C equivalent will be 1 divided by C1, 1 divided by C3, plus 1 divided by C24, everything to the power minus 1. We can do the calculation. So it will be 1 divided by C1, which is 8 microfarad. And this gives you how much? Oh, okay. Yeah. I made a mistake here. Okay, be careful. These two guys are in parallel. You add them. So C24 is not this, obviously. C24 will be 6 plus 6, so it will be 12 microfarad. Okay, so C24 is C2 plus C4. Okay, because they're in parallel. When they're in parallel, you combine them by adding them. Is it clear? Okay, so C24 is 12, so here it will be 1 over 12. Do you all agree? Okay, good. So here it's C2. Let me write it in another. But you need to be careful, okay? C2 plus C4. As parallel, you need to add them. Series is where you take the reciprocal. Okay, so C equivalent that we already calculated is how many? If you do this calculation and then you take it to the power minus 1, this will give you 3 microfarad. So the whole thing has a C equivalent of 3 microfarad. So as you said, C equivalent is 3 microfarad. That means we can calculate Q equivalent. So basically we have 12 volts across one equivalent circuit, the equivalent, which is 3 microfarad. So we can get what is the Q equivalent. It's just Q equivalent V, so it will be 36 microcoulomb. So that means here you will have 36 microcoulomb. Here you will have 36 microcoulomb because all of them are in parallel. And here you will have C24 and the total charge Q24 is 36 microcoulomb. Now C24 is equal to 3. No, we already calculated it. It was 12 microfarad. So we can calculate what is V24. So V24 will be Q24 divided by C24. So it's 36 microcoulomb divided by 12 microfarad. Micro will go away. So you will have 3 volts. This is V24. So here the voltage across here is 3 volts. So what is the voltage across C2? That's also 3 volts. So the answer is this. Great. Next. Now we have an electron, and I give you the speed of the electron. V is 2.65 10 to the power 7 meters per second. Enters the region of a uniform magnetic field B, and it moves in a circular arc of radius this. R is 0.2 meters. Question, what is the magnitude of B? We already talked about this, the radius is MV divided by QB, meaning B will be what? MV divided by QR. We know M, mass of an electron. We know V, it's given. We know Q. We know R. You do the calculation and you'll find 0.75 millitesla. Next problem. You read the problem. I'll let you read it carefully. You read it already? Great. So the question is, find the magnitude and direction of the net magnetic force on this wire. Okay, so here all what we have to use is F is IL plus B. So F, which is the net force, F net, is made of three forces. I'll call them F1 plus F2 plus F3. This is what I will call portion 1. So if you look here, we have a current, we have a magnetic field pointing outward. So the force here, if you use the right-hand rule or any rule that you want, the force will be here. This is what I call F1. This portion, I will call it 2. So this is portion 1. This portion is portion 2. You use the right-hand rule, it has the same length, same magnetic field. So F2 will be pointing up. And they're equal and opposite to each other. So this is F2. And you see that F1 plus F2 will just cancel each other. They have the same magnitude, Y, the same current, it's the same length. The length here is the same as the length here, and is the same magnetic field. So they have the same magnitude in opposite direction, so they will cancel each other. So effectively, net force is just equal to F3. So this is what I call portion 3 here. So the net force 3, you use the right-hand rule, and you will see that it will go to the left. So it's either this one, or this one, because it has to be to the left if you use IL cross B, okay, using the right-hand rule or Ampere's gentleman, le petit bonhomme d'Ampère. Then F3 is in this direction, and it's equal to F net. Okay, now in magnitude, what is F3? It will be ILB sine the angle between L and B, which is 90 degrees. So it's just ILB. So it's 6. What is L? L is, here I mean L3. Okay, the length of portion 3. And that in meters is 0.45 meters. So it's just this. This is 45 centimeters. You put it in meters. You multiply by B. How much is B? 3.22. You do the calculation and you get 8.69 Newton to the left. So it's this one, which is the right answer. Okay. 8.69 Newton to the left. Next question. I let you read the question carefully. It's an interesting one, and we solve it quickly. So you read very well this question, question 9. So a student keeps a 60-watt lamp on. This is not good for 12 hours, okay? Have to be energy responsible. Don't waste energy. Anyway, so the power is equal to 60 watt and it's turned on for 12 hours. So delta T is 12 hours, which is 12 times 3,600 seconds. So we know how many seconds is this. 12 times 3,600 seconds. This is delta T. We'll come back to it in a minute. So if the lamp was connected to a 120 volt power supply, find the amount of charge that passed through it during this delta T, which is given here. Okay, so this is the power. And you can look at the lamp as a light bulb, which is a resistor if you want. Okay, and then you find the power for a resistor is I square R is the same as V square over R, etc. So you can find R if you want. But we'll not do that. We'll just say that the power is 60 watt. The power for any electric device is the current passing through that electric device times the voltage across that electric device. So meaning 60 watt is equal to times I times 120 volts. So I, which is the current, is the power divided by the voltage, which is 60 watt divided by 120 volts. This gives you half an amp. So the current I is 0.5 amp. So if I want the amount of charge, Q is IT, if you remember, or I delta T. So the amount of charge that passed through the lamp for this 12 hours duration will be I half amp times T. What is T? 12 hours. And you do the calculation. This is your answer. 21,600. And this is the answer. Good. Let's look at the next problem, which is extremely important, and you have to read it carefully. Okay, so for this example or for this problem, you need to read it carefully and then we start solving it. So we have 4 identical capacitors, each having a capacitance of 4 microfarad. So we have, let me start writing from here. C1 is equal to C2 is equal to C3 is equal to C4 is equal to C, which is how many? 4 microfarad, 4. Okay, and it's written here. And they are connected as shown. A 10-volt battery is connected between point A is here, and point B is here. Question, what is the charge on capacitor 2? I want the charge here, Q2. For this type of problems, always try to go step by step, or you look for shortcuts, but it's better to go step by step so you'll not make a mistake. So let's find the equivalent capacitor step by step and by drawing. So I'll start by A, C1. So here you see that 2 and 4 are in series. So I will call it C24. So I will call here C24. And here I will have C3. And here I will have point B. So let's calculate C24. Come from C2 series C4. So basically it will be C2 times C4 divided by C2 plus C4. So that will give us C divided by 2, basically 2 microfarad. So this is 2 microfarad. Next. And this is equivalent to having A here. So here we'll have C1 And here I will have now C24, C24, excuse me one sec. So I said C24, 3. So you see C24 is in parallel with C3. Then I will have here B. A is here. So what is C24, 3? When they're in parallel, you just add them. C24 plus C3. So it will be 2 plus 4. That will give you 6 microfarad. And then this is equivalent to having A here. And now here I will have B. And here I will have C, 1, 2, 4, 3. Which come from C1, which is in series, is C243. So here C equivalent is C1243, and it will be the product in C1 and C243 divided by the sum. In other words, the C equivalent will be 4 times 6 divided by 4 plus 6. So C equivalent is 2.4 microfarad. So that's the C equivalent. Let me write it here. C equivalent is 2.4 microfarad. So this is equivalent to having this A, B, and here you will have C equivalent is 2.4 microfarad. Great. So if that's my C equivalent and the voltage between A and B is 10 volt, that means Q equivalent, which is Q 1, 2, 4, 3, is just C equivalent times V, which will be 24 microcoulomb. So we will have 24 microcoulomb. So here we'll have 24 microcoulomb. Okay, because plus 24 minus 24. Just put 24. Okay, good. But it comes in, so here, because they are in series, so it will have 24 microcoulomb. And here I'll have 24 microcoulomb. Do you all agree? Good. Now, having 24 microcoulomb here and having 6 microfarad, this gives me this voltage here. Let me call it V243. It will be the 24 microcoulomb divided by 6 microfarad. Micro goes away. So the voltage across here is how many volts? 24 divided by 6, it's 4 volts. So what is the voltage across here? It will be 10 minus 4, so it will be 6 volts. Or it will be 24 divided by 4. 24 divided by 4, that gives you also 6. Okay, right. So here we will have 6 volts. Here we will have 4 volts. Now what is the charge here? Well, if I want the charge on 2, it will be C24 times the voltage, which is 4 volts. So it will be 2, we all agree, microfarad times 4 volts. This gives us 8 microcoulomb. So the answer is 8 microcoulomb. So the charge on 2 here is 8 microcoulomb, and it will be the same charge as 4. It will be 8 microcoulomb. Yeah, because they are in series. Good. Next. Read the question carefully, and you calculate the magnitude of the torque on the coil due to B. You remember, look at your formula sheet. Torque is mu cross B. Mu is the magnetic dipole moment, and B is the magnetic field. So let's calculate mu first. Mu is NIA. Number of turns, current times the area. Area is given here. Number of turns is 3, current is 1. Now what's the direction? The direction, let's use the right-hand rule. So the direction, since the current is going in this direction, the mu will be downward. So mu is in the direction minus J direction. So this minus J hat, the negative Y direction. B is already given. This is my B. Okay. So let's do the calculation. The torque is NIA minus J hat. Minus J hat, I can write it as 0 minus 1, 0. Cross B. What is B? B is 2I hat minus 3J hat and minus 4K hat. I have to do this cross product here. So this gives me NIA. Now you have to do this cross product. So we will have 4 minus 0. Then we will have 0 minus 0 along Y, and along Z we will have 0 minus 1 times 2. So basically plus 1 times 2. So basically 2. So the torque is NIA, 4 along I hat, 0 along J hat, and 2 along K hat. Now let's do the calculation, because I want the magnitude of the torque. This is the torque. Now I want the magnitude of the torque. It will be NIA. Put the magnitude of this. This is 4 squared plus 2 squared. N is 3, I is 1, A is 4, 10 to the power minus 3 times square root of 16 plus 4. You do the calculation. The answer is this. Newton meters. Next question. You read the question carefully. Okay, so it's a resistor. So we know that the power for a resistor is voltage squared divided by the resistance. Let me use it for P1. I'll say that P1 is V1 squared divided by the resistance. And power 2 dissipated is V2 squared divided by the same resistance. So let's say P1 divided by P2. I will get rid of the resistance. I'll have it's V1 squared divided by V2 squared. This means that the power I'm looking for, which is P2, is P1 times V2 divided by V1 squared. So I know P1, it's given here, 0.54 watt. V2, well, is 1.5 divided by V1, which is 3 squared. In other words, the power I'm looking for is 0.54 times, so this is 1/2 squared, 1/4. So this gives you 0.135 watts. So for the same resistance, if I connect the same resistance to two batteries, one of the EMF of the battery is a double of the other one, I will divide the power by 4 because of this relationship. Next question. Let's read this question very carefully and we solve it. So we have a 1 meter long wire. I give you the length of the wire. The 1 meter long wire carrying a 1.56 amp current is laying along the x-axis. You see, this is the x-axis. The wire is placed in a uniform magnetic field. If the current is in the positive x direction, you see the current is flowing in the positive x direction. Find the magnetic field B in Tesla that will keep this 100-gram wire suspended in the air. So this is my wire. We will have two forces. The first force is a gravitational force, which is the weight, and the magnitude is mg. Now, what's the second force? I need to have a magnetic force. I have a current carrying wire in a magnetic field, so I will have a magnetic force, what we used to call in high school a Laplace force, okay? So the magnetic force, you remember, is IL cross B. So look carefully here. IL, look at L. L is along the x direction, I hat. Cross B. What should be the direction of B? Such that this magnetic force will cancel this gravitational force. You see the gravitational force is along the negative y direction. That means the magnetic force has to be along the positive y direction. So what should be the direction of the magnetic field such that the magnetic force is in the positive y direction? Use the right-hand rule or Petit Bonhomme d'Ampere or whatever rule you feel comfortable with. Anyway, I should know that the magnetic force should point upward here. And it should be equal in magnitude with Fg. We suspend it in air and it will be opposite in direction. So I repeat again, what should be the direction of the magnetic field if I want this to be along J direction? So that means this magnetic field has to be along the negative K direction. Do you all agree? The magnetic field B has to be along the negative K direction, the negative Z direction. So either this is the correct answer, either this is the correct answer. It has to be along the negative Z direction. Do you all agree? Because I want them to cancel each other. So this FB has to be opposite in direction to FG. Now in magnitude, they have to be the same. FB has to be FG. which is mg. So ILB sine 90 degree, which is 1, is equal to mg. That means B is mg divided by IL. All what I have to do in order to solve this problem. Now you do the calculation. You know M 0.1 kilogram. The mass is this. G 9.8. I 1.56. L is 1. You do the calculation and you will find that D is the correct answer. So the magnitude is 0.628 Tesla, and the direction has to be minus K. So B is along the negative Z direction. So this is the right answer. Is it clear? Some good students missed this question. Okay, good. Now let's look at question number 14. Question number 14. Find the drift velocity for electrons in a wire which has a radius of this, carries a current of this. So this is R, 0.1 10 to the power minus 3 meters, and I is 2 amps. The number of atoms per unit volume is this. And there are 2 free conduction electrons per atom. In other words, I'm giving you N, which is the number of free electrons, per atom, or per unit volume. So the number of atoms per unit volume is 6, 10 to the power 28. This is the number of atoms per unit volume, but I have 2 free electrons per atom, so I have to multiply by 2. So N, which is the number of electrons per unit volume, is 12, 10 to the power 28. 3 electrons per meter cube. Great. Now the question is, find the drift velocity. How do we find the drift velocity? Well, I can use the fact that J, which is the current density, is I, which is the current divided by the cross-sectional area, pi r squared. But we also know that J, which is the current density, is N, which is the number of free electrons per unit volume, times E, which is the fundamental charge, times VD. So using this, I solve my problem. VD is I divided by pi r squared divided by NE. We do the calculation. 2 amps pi r squared, 0.1 10 to the power minus 3 squared, 1 divided by N, we already know N, 12 10 to the power 28, times E. E is 1.6 10 to the power minus 19 Coulomb. You put everything in SI units, so how much do you get? So the right answer here is this, E. (3.3 10 to the power minus 15 to doing this calculation. I hope it's clear. Let's go to the next problem. As you notice here, the radius is 1 millimeter, not 0.1 millimeter. So I made a mistake, okay? I guess I'm tired, okay? So the radius is 1 millimeter. So the radius is 10 to the power minus 3 meters. So here also so it's 10 to the power minus 3 meters. So it's 1 10 to the power minus 3 meters. And you do the calculation properly and you will find E is this, okay? 3.3, I mean VD is 3.3 10 to the power minus 5 meters per second. Okay, so you use this formula, put everything in the right units, and you make sure that you don't make a mistake on the radius. So the radius is 1 millimeter, not 0.1 millimeter. As I said before, it's 1 millimeter. Next question. So an electron, and we know the mass of the electron, we know the charge of an electron. It's in the formula sheet, and you know it by heart. Enter the region of uniform magnetic field with a velocity. So the velocity is given. V is 1.5 kilometers, so 1,500 meters per second along the direction I hat. At that instant, it experiences a magnetic force, FV. And FV is 2.25 10 to the power minus 16 Newton in the direction J hat. Find the magnetic field. FB is QV plus the Lorentz force. So FB here is along the direction J hat. Let's check. Q for an electron is negative. Here I'm just looking at the direction first. No, what should be the direction of B? So Q is negative, so I put negative. V is in which direction? I hat. So negative I hat cross. Now what should be the direction of B such that this will be true? So the direction of B should be K. Do you all agree with that? Yes, because if you say I cross K, this gives you minus J hat, and then you put another minus, so minus minus gives you plus J hat. So you know that for a fact. B, in order to have FB in the direction of J hat, and we know that V is in the direction of I hat, B should be in the direction of K hat. So B is a positive number times K hat. So either this one or this one. I will not choose this one. It's negative K hat. I will not choose this one, negative K hat. This is also false. So it should be in the positive direction, positive Z direction, in the direction of K hat. Now, how do we get it? Well, in magnitude, we will know that FB in magnitude is absolute value of Q, V, magnitude of V, magnitude of B, times the angle between V and B. So who can tell me what is the angle between V and B here? Should be 90 degrees. So that means B is FB divided by QV. We know FB, 225 10 to the power minus 16 divided by QV. Q is 1.6 10 to the power minus 19, and V is 1,500. Everything in SI units. And once you do that, you find a magnetic field B, which is this number here. Okay, so B is 0.938 Tesla in the direction of K hat as expected. Last question. So a parallel plate capacitor has a plate area of this. Okay, you remember parallel plate capacitor, of course. Parallel plate capacitor. Earlier, we talked about a cylindrical capacitor. I could have given you a spherical capacitor. This is a parallel plate capacitor. So this area here, call it A, is 0.3 meters squared. Plate separation is D, 0.1 millimeter, 10 to the power minus 3. So the charge magnitude on each plate is 5 microcoulomb. So Q here, so here we'll have, let's say, plus Q, 5 microcoulomb. Here we'll have minus Q, which is minus 5 microcoulomb. Question, find the energy density stored within this capacitor. So we want to find the energy density stored in this capacitor. Of course, the energy is stored in terms of magnetic field. Electric field, sorry. The capacitor energy stored in electric field. If it was an inductor, energy stored in magnetic field. So here, the energy is stored in electric field. As you can see, the electric field will be pointing in this direction. And we will have our energy density stored in terms of electric field. So the energy density U, we can calculate it two ways. It will be half epsilon naught electric field squared. This is one way to calculate it. Another way to calculate it is, we will say the energy, electric potential energy, divided by the volume. And the volume here is A times D. Both will give you the same answer. Okay? So what is the potential energy? It's half C squared. Or you can say it's half Q squared over C. So choose what you want to use, but all these formulas will give you the same answer. So let's say I'll choose this one. It will be half Q squared divided by C divided by the volume, which is A D, the volume between the plates. So it's half. Do you know Q? Yes, we know Q. 5, 10 to the power minus 6 squared. Do you know C? Well, it's a parallel plate capacitor. We know C, that C is equal to epsilon naught A divided by D. We divided by epsilon naught A divided by D. And then we divide also by A D. So the D goes away. We will have half 5, 10 to the power minus 6 squared divided by epsilon naught 8, 8.5, 10 to the power minus 12 times A squared, which is 0.3 squared. Let's do the calculation quickly and give me the answer. So the answer is 16 joule per meter cube. It's the density, it's an energy divided by a volume, so it's 16 joule per meter cube. So C is the right answer. Okay. We could have solved it by saying, for instance, that U is half epsilon naught E squared. But what is E? Well, E, it's a parallel plate capacitor. So each plate is a conductor. So it will be sigma divided by epsilon naught. That's E. But what is sigma? Well, sigma is Q divided by A divided by epsilon naught. So that's it. So this will be half epsilon naught. Instead of saying E squared, I would say Q divided by A, which is sigma, divided by epsilon naught, and this squared. And this will give you the same answer. Okay, and this is half Q squared divided by epsilon naught A squared. And that's what we calculated already. The answer is 16 joule per meter cube. Okay, that's it. So make sure that you know how to solve this for the makeup exam, especially for those who are sure that you'll go for a makeup exam. Understand what's going on, and yeah. So I wish you the best and see you later. Bye.